our exploratory methods for trying to modeling the couple with the information that we could get from the from the TTS survey. I will start with the and the whole modeling of carpooling is within the GTA model framework, which is then an agent-based and activity-based travel demand modeling to model the travel demand in the Greater Toronto and Hamilton area. And I will start with the definition of carpool in the current model system. So what the current carpool is referring to the inter-household carpooling, which means the sharing of a private vehicle by people from different households. And there are it is important because there are many benefits attached to it. So one of it is it could extend the mobility for dependents and as well as reducing the need to use multiple single occupancy vehicles, which may lead to more traffic congestion. And some of the background information about the current mode choice module in Tasha framework in the GTA model is that the current couple mode is one of the auto passenger modes as showing up here in the slide. And it is not the PTC or taxi, which is running by the private vehicle companies. And we have more specific cost and wait time attaching to those two modes. And currently, the value of time of the carpooling is based on each individual's demographic category, whether you are a professional worker, a general worker, or non-worker, non-students tab. And compared to, so currently the travel cost of that carpooling mode is the same as the other auto passenger or auto driver of the same auto cost. So when we're trying to run the counterfactual scenario last year to test if without PTC, what would the travel demand switch to? And we found that a majority of the demand is switching to carpool because it is a relatively cost-free mode compared to the other transit or compared to other transit modes. And also currently in the model specification, the couple passenger are not assigned to any drivers or vehicles. So there is no constraints from the driver supply side to say whether, oh, this couple is feasible or not. So that is what we want to bring to better modeling the couple in to improve it in the GTA model system. And ideally, the travel demand of carpooling is from your, like, for example, your colleagues, the members from the same, your classmates, your extended families, like your grandparents helping you, picking up, dropping off the grandkids. However, the current TTS or all the typical travel survey information we have is mostly household-based. So we know little about, almost no information about the inter-household information, interactions relating to this. So we have to abandon that idealistic way for now because we don't have enough sufficient data to develop that social network model. And it is also quite computational intensive and contextual based. So what we have is we still want to improve the mode choice model of carpooling. And what we have is the information from the TTS survey, which captures the carpooling trips from separately passenger and driver side. So we know that from the passenger side, there is an auto passenger, there is a person reported an auto passenger trip, and we know that he or she is not receiving that ride from the household members, because we know all the information of their trip information of their household members. So we could exclude those intra-household trips and identify those carpooling passenger trips. And using the similar method, we could identify those auto driver trips who report traveling with passengers, but the passengers are not their household members. So based on the separate identification method, we could kind of take a look at the market share of the couple, which is relatively marginal, as around 4% among all the trips that captured in the TTS survey. And however, and we could say that it is around 1/4 of all the auto passenger trips and less than 1/10 of all the auto driver trips, which means that if we could get more if we were able to get more of those trips being matched, it could act as a lever to reduce the traffic congestion. So what we are trying to do is we examine those carpooling behavior in terms of the personal, household, and trip-based characteristics to kind of improve our mode choice model specification of the carpooling mode. And also, we want to bring some supply-demand constraints through building or developing a matching algorithm and in the agent-based modeling framework to identify the feasible matching pairs and as an constraint to the carpooling mode. And we start from looking at the individual and household attributes of both the passenger and the driver side. I wouldn't go into more too detail. And also another key information we take a look at is the trip characteristics. And what is relatively interesting and intriguing is that we found that from the separate demand and supply side of the drivers, of the identified carpooling drivers and passengers trip, they're kind of similar in terms of spatial and temporal patterns. So that also brings to the idea if how many of those trips could be matched, and if more trips could be matched, meaning that there is a huge potential to encouraging or triggering more use of triggering the usage to a more extent. And so we also take a look at some key matrices relating to this couple behavior, which includes the pickup distance, the drop-off distance, as well as the detour ratio, which is the overall distance a driver drive to pick up the passenger, travel together with the passenger to the destination and drop off the passenger, the overall distance divided by if without picking up the passenger, the direct or the distance of the driver. And we will using those key matrices from the TTS data to build our matching algorithm to screening and find the feasible pairs. So in terms of different matching methods that being used in the current agent-based modeling framework, so all of the methods can be characterized into the two groups. So on the left side, it is the agent level matching which includes match at a specific individual level, and based on the similarity in terms of socioeconomic profiles or past compatibility, and build a utility score based on those. And the output of it is an one-on-one match. And the typical method is typically the grading method, Hungarian method, so all those bipartite matching methods to match specific drivers to specific passengers. However, this method is relatively too data and compute intensive when we're trying to join into our agent-based modeling framework, because what we are currently matching is millions of drivers with millions of passengers, and the feasible pairs would be a multiply of the two sides. And so another way is a mass matching, which is relatively efficient, which is a relatively efficient way, but still could reflect the supply-demand feasibility between the drivers and the passengers. So what we proposed is a combination of the two. So at the agent level, we want to use the information we could get from the TTS, use the agent level constraints to filtering out those feasible pairs that could be matched, and then applying a matching algorithm and apply the mass matching to calculate an aggregated matching and getting a relatively efficient term to enter into our utility function. So all of those driver and passenger pairs would go through the screening process, and then the result would be the feasible pairs that passing those rules. And then we would also calculate a matching utility to reflect the quality of each driver-passenger pairs. And then the next step is for each of the passenger, we would get an aggregated attractiveness, which reflected by the SP in the formula. This is a matrix that could reflect both the quantity and the quality of the feasible matching pairs. And then we would calculate the matching probability based on the aggregated attractiveness of the driver-passenger pairs. And we're adding 1 to the denominator because the 1 represents the outside option of there's no feasible matches at all. And so the last step is that we want to incorporate that matching term, which could reflect the feasibility of driver-passenger matching into the utility function to better represent the couple mode. And also the descriptive, we also would get some, we also would like to get better representative of the individual household and trip characteristics of the carpooling trips from the descriptive analysis that we did before. So we're still working on incorporate that methodology into the GTA model framework. So it might be a wave 5 version improvement, so not yet being incorporated. However, today I want to present is the methodology that we want to approach. And so to conclude, or to summarize, carpooling is relatively a marginal mode, but still important because if we look at the distribution of the trips under certain time and special constraint, we found most of the trips are actually matchable based on our test result. Around 32% of the trips are matchable. So if we could encourage or improve the social network between drivers and passengers, so it could be a potential lever to mitigate the congestion, especially during peak hours. As we say, most of the carpooling trips are still happening in the AM and 2M peaks. And what we propose here is a relatively computational method of matching framework to represent both the constraints between the drivers and passengers, and trying to get a matching algorithm to improve the mode choice specification of the carpooling mode. And another ongoing work we are still trying to solve, or even though we don't have enough data to solve, is that whether carpooling is the availability of carpool for individual person, because what we currently model is the feasibility of a carpool. So if you are a passenger, and whether there will be a driver that is feasible to facilitate you due to the time and special constraints. However, whether carpool is a realistic option in your choice site is still hard to model in the current framework, and we may require further information of it in the future. Yeah. I think that's it, and I'm open up to questions.
So Gopar. My question is, in all the times I've done carpooling, it has been with people that I work with or I do some activity with at the destination end, rather than people that I carpool with from my social network. So if you had the best data available, do you think you would make it develop your models to be destination oriented? And if so, like, how would you do that?
Yeah, because currently we are trying to limit this. We are trying to constrain the destination by a more strict rule. So that could partially answer your question. And also we are currently matching those supply and demand based on similar destination purpose. Yeah, but if we could get better information, maybe from some carpooling platforms of how those demand, how those purpose are really matched, that would be better to improve that matching algorithm. Yeah.
Are there any questions online? How do we change that?
If there is a question, this part will get that. I have no questions so far. This is for the previous session.
That's a previous session?
Yeah.
Yeah, we don't have any online questions so far.
Any other questions for those in the room? Otherwise, I have one more. Because I'm curious. So actually, I was a little surprised when I saw how much single drivers have gone down from 2016 to 2022, and ride sharing and carpooling has gone up quite a lot. And do you think it's because of congestion or parking costs, or do you think it's because of car ownership costs, or something else?
Yeah, I want to bring another information that may relating to that, which is not relating to parking costs. It's because in the 2016 to TTS, what we captured is all the trip-making population less than 10 years, more than 10 years old, which means that 11 years old is the minimum age we capture. However, in the 2022 TTS, we have those aged 5 and above captures. So that may minimize the proportion of auto drivers in the overall
Most how many drivers in that age category?
Yes. Yeah.
Okay. Good answer. So it's mostly a data thing, you think?
Yeah.
Okay. It looks like there is a question in the chat.
It's more of a response from Professor Eric to you, Professor Matt.
Okay. All right. Well, reply to Matt. Yes, carpooling is very much a social network problem. Traveling with workmates taking a relative to the doctors, going shopping with a friend, etc. The challenge is lack of data about these social networks. Thank you, Eric. And thank you, Yagao. This has been a very interesting presentation. Thank you very much. Next up, we have Shuyan Zhu, who's going to be presenting spatiotemporal insights into ride hailing, what happens when we restrict driver supply. But before I pass the floor to Shuyan, I'm going to read a little bit about him. Shuyan is a PhD candidate in transport engineering here at University of Toronto. His research focuses on modeling driver retention and spatiotemporal supply dynamics in ride-hailing platforms. Oh, are we offline?
I'm looking for his presentation.
Oh, okay.
I'm sort of
Well, I'll keep saying things about him until you find the presentation. If you still haven't found it, I'll make some stuff up. He uses deep learning and survival analysis as his methods. He's passionate about integrating data-driven methods with urban mobility system design. But I think his greater passion is cats. And he has a cat that can play fetch better than other dogs can. So I'd like to hear more about that too. Are we ready to go?
Yep.
Okay, so please give a round of applause for Shuyan. Okay.
This is not working.
Okay.
Okay, yeah, so hello everyone, thanks for being here. So today I will present my research on the spatial temporal insight into the ride-hailing systems. In particular, we want to predict what happens when we restrict the ride-hailing driver supply. So I will start with a very brief introduction, and then I'll walk through the study area, the spatial temporal insight, and also the how we do the scenario evaluation. So to begin with, so ride-hailing service, just like Uber and Lyft, have improved accessibility and convenience to the transportation network. For example, if you want to go to somewhere, you can just call an Uber. It will provide a door-to-door service to you. And but this on-demand service can harm to our network, especially their rapid growth has created serious urban challenge. And studies have shown that they have accounted around half of the added traffic congestions and nearly 2/3 of the added vehicle miles and around 30% of emission from empty driving. And at the same time, those ride-hailing drivers do suffer from that. So they usually get paid relatively low. They get around, according to a report from the Ride Justice, we can earn around $6 to $10 per hour. So this issue highlights the need to better manage the supply side, especially how they join, stay, and leave the platform, and which is the focus of my research. So in our study area, we choose City of Toronto, and we use ride-hailing record from from Uber, Lyft, and Faith Drive in 2020, which is a pre-pandemic period. So the dataset covers all the platform dataset, and it includes around 22 million record and around 40 million trip. And to enrich the analysis, we also integrate the location data. And then because there exists some multiple activities for the drivers. For example, he might log in on both Uber and Lyft, and when he receives a trip request from one of the platform, he will log off on the other platform and working on the trip. So we conduct a deduplication process to address those overlapped records. And after the deduplication, we cleaning the final dataset contain 51 million idle event and 41 million trips. So before we start, we conduct a spatial temporal analysis regarding the ride-hailing service. For example, as you can see in the figure, we plot the completed trip on the weekdays, and here we visualize the hourly demand, and we can see that there is a very clear peak in the morning rush hour, which is
So the people online can hear you.
that it's very clear that we have a morning peak on the morning rush hour, and we have an afternoon peak in the afternoon rush hour. And for the daily distribution, it can be seen that the ride-hailing demand peaks on the Friday and Saturday. So which means that during Friday and Saturday, there are more ride-hailing service happening. And when we take a look at the weekend completed trip, and we can see a very different pattern regarding the weekday compared with weekday, because we don't have the morning rush hour, and we don't have the peak for the morning section. And we have a relative steady trip demand during the afternoon, and it lasts until the midnight. Let's move to the after introducing the demand side, we want to take a look at the supply side to see how if they consistent with each other, to see how the performance of the ride-hailing platform in managing the supply side. And we can see that we see the same peak during the Friday and Saturday. So regarding the supply side, also supply peaks during Friday and Saturday to service those demand. And we also plot the heat map for the percentage of drivers. It can be seen that we haven't seen, like we can see a very clear peak during the afternoon peak hour, but like during the morning section, like this peak is not very clear, which means that the driver are not willing to get up early to service those demands, and maybe because they have other arrangement during morning, or maybe because of their lifestyle, they just don't want to get up too early to like service other passengers. And we have also contribution for the working hours, the daily working duration for the ride-hailing drivers. It can be seen that most people doing, most the ride-hailing drivers are part-time, which means that they are working time, like half of them, the daily working duration is less than 4 hours. So most of the ride-hailing drivers are the part-time drivers. And turning to the performance metrics, it can be seen that the because we during the midnight, especially the early mornings from 3 a.m. to 5 a.m., the trip is longer compared with the other period. And during the morning rush hour, time for driver to pick up the passengers. Oh, sorry. And in the regarding distribution, it can be seen that the service quality is better in the downtown area. So like, you know, there are more demand in downtown area compared with suburbans. And regarding the driver wait time, the service quality is consistent across the city of Toronto. And finally, we want to explore these demand-supply interactions to see if we could find any gap in those metrics. So we define a metric called demand-supply ratio, and the demand-supply ratio is the indicator which demand over supply, and this how many demand should a driver service. And it can be seen that because we have said that during the morning rush hour there is a clear peak for the ride-hailing demand, but there isn't a clear peak for the ride-hailing drivers. So it can be seen that we have more demand compared with supply during the morning rush hour, and we also have more demand during the Saturday and Sunday midnight. So in those periods, we have more passengers, but we don't have enough driver. So, and we have also defined the heat map for the active trip time ratio. It can be seen that for those periods, when we have more drivers, the active trip time ratio is higher. So, which means that the driver can make more efficient service compared with other period because there is less driver and more passengers. So they don't need to spend time idling on the road network or spend time doing some cruising to try to get trip request. Similarly, the idle distance downtown area we have better system efficiency, and for the alteration the idle distance ratio. The driver might need to cover more distance to pick up the passengers. So it is clear that we have compared the demand pattern, the supply pattern, and their interactions. So now we want to know if we can reduce some supply to see how the system evolves. So we use the agent-based modeling framework for the ride-hailing supply modeling. We build the ride-hailing driver agent and to evaluate how the different number of drivers will affect the system performance. So, for example, what if we cut some of the drivers? What will change? So we use an agent-based model. The agent such as passenger, driver, platform, and environment. The passenger have the state variables called origin, their destination, their trip request, which are all retrieved from the historical record. And driver, we have the exit risk, which is retention, which is function that to describe their decision to stay on this platform. And it is affected by fares. And also we have the decision to log in or log out. And the logging decision has been determined by the historical record. And also we have the platform. The platform decides the pricing for each trip event, and also the dispatching mechanism, because we know that the ride-hailing companies such as Uber or Lyft, they use a very complicated matching algorithm to match the demand and supply. So here we use greedy algorithm because it is the most adopted mechanism. And the last, we have the environment, which decides the travel distance for each trip, and the state variable has been determined by the GTA model. So which is basically we use the zone-to-zone. And for the scenario we want to evaluate is the two scenarios. If we want to reduce supply, license cap, or we can adjust the fare so that there will be less drivers. And for the system performance, we want to see the performance of how the passenger waiting time, the vehicle waiting time, and the utilization change. We built the simulation and we calibrate user real data from the from City of Toronto in January 2020, and we implement features such as adding the drivers, removing the drivers, and we have compared the simulation compared with the real world result, and it can be seen that those are very similar patterns. So, which is the calibration process of our simulation. And these calibration results fit very well with the observed attribute. We want to first to test the license capping, and second to test the fare adjustment. Here we we reduce supply levels, and from 10, here we will contain 10% driver and we have 10% drivers, we have 20% drivers, 70%, 40%, like to 90% drivers, and we have different metrics such as passenger waiting time, driver waiting time, utilization, and refusal rate. And it can be seen that if we contain 70% of drivers, the utilization for the system is highest, which can be seen as a near optimal utilization rate. And it suggests that now we have oversupply conditions. And we have also compared the impact of pricing levels, and since a higher base fare or a higher fare will reduce driver working duration. So we try to this fare by using the develop a linear regression model to the ride-hailing platform event logs, and it can be seen that if while the fare adjust, such as surge pricing, may not translate one-to-one into the driver earning due to the platform commission rule and the dynamic incentive. We can see that when we reduce the price of the fare, the utilization is decreased because the drivers spend more time on the platform to earn money. And when we increase it, the system utilization has increased because driver could, when they receive enough money, they will exit the platform. And this happens just because for now it is oversupply conditions in the city of Toronto, and and for the pricing levels for cost per kilometers, we have the same issue, and it shows a nonlinear relationship. So, which is suggests that for now, in city of Toronto, we have oversupply condition compared with the demand that we have, and our agent-based modeling result has revealed that if we use some control methods such as license capping or fare adjustment, could help improve the system efficiency. Yeah, thank you for your listening, and yeah, I'm open to any questions.
Thank you, Shuya. Questions? Oh, hold on. One moment.
Thank you, Shoyan, for the presentation. It was great. I was wondering when you talk about supply limitation and knowing that we have different profile of drivers, we have those who work part-time and those full-time. How do you feel like this utilization would be applied? Are we talking about like any driver, or we are talking about capping the supply for full-time drivers or part-time drivers?
I mean, I think, so in my simulation, I cut them randomly. So basically it's like we haven't distinguished the part-time driver and full-time drivers, but we are thinking about like if there is a license capping, let's say if City of Toronto impose a license capping, I think most part-time driver will quit the job instead of the full-time drivers.
Other questions? I have a question. Do you think that most of the ride-hailing passengers are residents of Toronto, or is there a large proportion that are tourists and people who are visiting and would behave quite differently than the people in the city who live in the city and who are represented in surveys like the TTS?
That's a great question. Like, yeah, I agree that leisure purpose is a very important. Like leisure activity is very important for the ride hailing. I think around 20% of them are for leisure. Like, and so now we are using the data from provided by City of Toronto. So it's not like TTS data. I think TTS data have the their trip purpose, like who they are, and so I think if we can utilize that part, we might be able to differentiate different trip purpose. Yeah.
Thank you. Any other questions? Are there any questions online?
Not yet.
The question at the back. Let me.
For your maps you showed earlier in the presentation, there was a really quick pickup time for a lot of rideshare users in downtown Toronto. And I mean, I live downtown as well, but I know that the transit availability and reliability, not always, but usually is pretty good in that same region. So I'm wondering, from the information you have, are a lot of those rides local with like downtown to downtown, or is it people flowing from downtown to within the city of Toronto, but like a more suburb area, or even out of town, or how do you explain that?
Sorry, could you repeat? I'm a bit confused. It's like, yeah.
What I saw was downtown, there's a really quick pickup for rideshare users. And I'm curious, are those rides going from downtown to downtown, or downtown to the further reaches of the city, or out of the city? And do you think that, this is a two-parter basically, do you think that improving transit service would have an impact on that or not?
That's a very good question. It's like, oh yeah, that's a very good question. Like, I think, yeah, I like you as asking like if ride hailing has complement effect or competition effect to the public transit, right? So
Yeah, that's a much better way of wording my question.
yeah, like I think from the research, like did like we believe that in like they do substitute some transit trip, like some trip that could have been you take public transit, like, but in general, like the complement effect is more than the competition effect. Yeah.
Okay, good to know. And then kind of just real quick, just kind of add to it. Do you know if that complement or competition effect is greater or less within short trips downtown or within longer trips? I guess I didn't scope, so I apologize for that.
Oh, I think it's those complementaries is great in the longer trip, especially like people they might oh, that's a very good question. Like they might take Uber to some transit station, like and then take transit station. Yeah.
Thank you.
Cut off questions there because we have to keep going with the agenda, but thank you very much. To Shuyan. Our third presenter is Alia Galal. Alia is, as of just a few weeks ago, a postdoc at University of Toronto, just graduated with her PhD. Her research is multidisciplinary, combines urban freight transportation, human factors, driver training, traffic safety, and the research that she's going to be talking about today assesses and improves drivers' hazard anticipation skills with the larger aim of enhancing safety of interactions between trucks and vulnerable road users in urban areas. Alia did not provide me with a fun fact, but I know something about Alia because she was my PhD student. She has a daughter whose name is Malak, just had her birthday last Friday, 10 years old now. You didn't know this, but she submitted her PhD application and I've accepted it. So that's the fun fact for you today. Congratulations to Malak, their newest 10-year-old PhD student. 7, oh. Oh, I better change my mind then. She's too young. Let's take my phone.
All right. Hi, everyone. You might think that this presentation doesn't really fit in the agenda of today's sessions, but it's actually the missing puzzle piece, so to speak. So, because I really think that reducing congestion, reducing emissions, improving the transit system, and all those topics are very good. However, I question whether anything would be worth it if safety is compromised. So here I am with my last piece of the puzzle, talking about safety. So I like to start my presentation with this graph here from the MTO. It's a little bit old, but it shows with the bars, it shows the road fatalities that happened over the year in roads in Ontario. And the line over there on the top shows actually the proportion of pedestrian fatalities. So the good thing is that the overall fatalities tend to decrease, shown by the bars. However, the proportion of pedestrian fatalities is increasing. So we see quite an important issue there. Truck collisions specifically are a very fatal and very severe type of collisions, and they get more severe and more fatal when pedestrians or cyclists are involved. So from now on, I'll call pedestrians and cyclists vulnerable road users. In some countries, cyclists killed by truck accidents or by trucks represent up to 30% of all cycling fatalities. So this is quite a high number. And research has also proven that human factors and human errors specifically significantly reduce truck safety. And in more detail, driver errors and driver distractions are found to be the most common cause for truck collisions. Hazard anticipation is one of the very frequent errors that happen, especially when drivers are novice or young, so they don't have enough experience. There is a remarkably small number of studies that focus specifically on how to improve this specific skill, which is hazard anticipation. For example, there are several studies conducted at different universities that involve the use of truck simulators. However, none of them actually tackles the problem of improving vulnerable road user safety. So as part of my research, we identified several gaps, and then we conducted several studies just to address those gaps. So the first gap, or the very general gap that we identified, was that the effect of human factors on truck vulnerable road user safety is actually quite understudied. So this is why we conducted our first study, which is a scoping review study on the effects of human factors on truck vulnerable road user safety. Now, according to the findings of this first study, we identified that vulnerable road user safety training is actually also very much understudied. So we decided to conduct the second study, which examined subject matter experts' views and opinions on vulnerable road user safety training. So we interviewed a couple of truck professionals, or like truck driving professionals and road safety professionals, to give us more insights. And then from those two studies, we identified a need for more behavioral studies that assess how to implement vulnerable road user hazard anticipation training, and whether this type of training actually improves the behavior of truck drivers. So I'll guide you through those 3 studies in more detail. So the first study is, as I mentioned, a scoping review, and we had 3 objectives in mind when we conducted this study. First, we wanted to generally identify all the human factors that are involved in truck vulnerable road user collisions. We wanted to examine the methodologies used in research, and we wanted to identify any needs for future research. So the scoping review followed the PRISMA guidelines for scoping reviews. So it's a very meticulous process to identify studies to include in the literature review or in the scoping review. So we conducted a systematic search on 5 engineering databases, and we, out of about 5,000 studies, we identified about 24 that met our inclusion criteria and got analyzed in this scoping review. We divided our 24 studies into 2 groups based on the type of data sets or the type of data used in each group. So studies in this topic area were based on collision reports or road user behavior and opinion studies. And both groups actually used specific methods. So for example, modeling techniques and descriptive analysis was used to analyze collision reports, whereas simulator experiments, surveys, and focus groups had more details about human behavior in general. In a very quick summary, those are the human factors that we identified that play a major role in truck vulnerable road user collisions. So, of course, vision issues from the truck cab driver, as well as vulnerable road user age, uncourteous road user behavior, training and education, and, of course, driving and cycling experience play a great role. Very fast, the implications of this scoping review are that we are in desperate need for more behavioral studies, where we look at the driver behavior in more detail, like how they press on brake and accelerator pedals or where they look at. And we also identified a need for studies on the effect of driver states, like whether they're distracted, fatigued, tired, sleepy, and also the effect of different training types on safety. We then moved on to our second study, which is a subject matter expert interview study. We also had 3 objectives in mind when we conducted this one. So we wanted to gather opinions and feedback on the current training, how Ontario schools, truck driving schools, conduct their training, what they teach their students, and so on. We also wanted to interview subject matter experts on the need for including vulnerable road user safety as part of their training. And we wanted to gather several hazardous scenarios with vulnerable road users that they faced on the road. So because it was COVID, we conducted 21 virtual interviews with subject matter experts, and those included novice and experienced drivers, as well as trainees and other road safety professionals. And we asked them open-ended questions about the use of simulator in training, the potential for adding vulnerable road user safety component in training, and so on. We realized out of those interviews that current training in Ontario for truck drivers actually lacks a focus on vulnerable road user safety. However, our interviewees highlighted the need for including it in their entry-level training. When we asked them about the use of simulators, those who received simulator training as part of their training actually endorsed it and had very positive feedback, although some issues also arise, such as poor graphics or some of them experiencing motion sickness or simulator sickness. And among the hazardous scenarios that we collected from this study are navigating intersections and turns, parking and backing up, and several uncourteous vulnerable road user behavior. So among the implications out of this subject matter expert interview study, our interviewees mentioned that training needs to be longer and more practical. Vulnerable road user safety related components should be added to current training. Simulators, as I mentioned, were strongly endorsed, and several hazardous vulnerable road user scenarios were gathered. We also came up, or like the interviewees came up with other policy and regulation implications that do not really fit with this, with the scope of this interview, but are generally very insightful. Now, moving on to the third study, which is the simulator experiment study, we had two main objectives in mind. First, we wanted to develop a training component that tackles truck driver hazard anticipation skills that relate to vulnerable road users. And then we wanted to measure the effectiveness of this developed training module on driver behavior. So the training that we developed was actually divided into two parts. One, like both of them are video-based. The first one of them was a theoretical video where we explained what hazard anticipation is, what common scenarios for what hazardous scenarios might arise on the road and so on. And then our second part was a video also, but it included 4 scenarios where the screen would freeze right before a hazard would materialize, and then the participants or the trainees would get some time to think about how they would react and how they would behave in the coming few seconds to avoid the collision. So the simulator experiment worked as follows. So when participants arrived to the lab, we gave them some instructions. They signed a consent form, and then they started off with a few practice drives just to get them more comfortable with the driving environment in the simulator. They then conducted 2 pre-training drives on the simulator that included 4 hazardous scenarios. They then either took the hazard training that we developed or a placebo training. And then they carried on with the second part of the simulator experiment. And then they had to answer a few questionnaires. For this experiment, we included 26 participants. They ranged in age from 21 to 64, and they were either current trainees still receiving their truck driver training or novice drivers that graduated within the last 5 years. This is a video of from the eye tracker that we used. So this red crosshair is actually the pupil, where the pupil of the driver is located at all instances. And then this is the interface that we worked a lot with to come up with our data. In terms of results, we looked at several glance measures, so where they look at. So the percent time looking, how much percent of their time they look at areas of interest or like hazards on the road. And we do see a significant improvement after hazard training. And then we also looked at the average glance duration and the maximum glance duration towards hazards before and after training. And we also see significant results or significant improvements on those metrics as well. We also looked at several driving metrics, such as the average speed and the maximum deceleration, so harsh braking. Although the results aren't statistically significant, we do see some improvements for the hazard trained group after training, as we can see from the box plots over there. So this simulator experiment shows that the vulnerable road user hazard anticipation training module that we developed actually leads to certain improvements in terms of glance behavior. Although we didn't see any statistical significance on driving measures, we believe that more data would provide more like better results on those measures. And from our questionnaire data, our participants highlighted that entry-level training and licensing exams should include a component on vulnerable road user safety. So overall, this whole research in general provides human-centered comprehensive investigation on truck vulnerable road user safety in Ontario. So it combines literature, subject matter expertise, and a behavior analysis on the behavior of truck drivers with respect to managing vulnerable road user hazardous scenarios. We also provide recommendations for truck driver training, and we do apply theories of hazard anticipation and visual attention that we gained from passenger vehicles, and we extend them to trucks. So overall, we do see and we do highlight critical gaps in behavioral studies in terms of truck drivers and vulnerable road users. And with that, I conclude my presentations and I'm open for questions.
Do you have any questions for Alia? You want me to ask the questions because I just finished her PhD exam and I have all sorts of hard questions.
Thank you, Alia, for the presentation. The question I'm having is about the hazard examples that the driver were exposed to. So in the pre-training, they were presented with these hazard examples. Is it the same example for the post-training as well? Or in the post-training, they were just having like a different sort of like a hazard environment? Because if they see same example before, I would say like they would be better in anticipating it.
No, so thanks for the question. No, so we had a total of 8 hazardous scenarios. They watched 4 before training and 4 after. And then we also, just so that people don't have this learning effect, we kind of counterbalanced the order of the scenarios. So not everyone received the same 4 before training and 4 after training. They were actually counterbalanced. So they never drove the same scenario twice.
So is it the same type of scenario with cyclists or there's pedestrians, any sort of?
It's a mix. So we, out of the 8, we had 4 pedestrian scenarios and 4 cyclist scenarios. So we divided our 8 scenarios into 4 drives. So 2 drives before training, 2 drives after training. Each drive had 2 hazardous scenarios, 1 pedestrian and 1 cyclist.
Thank you.
Other questions? Well, I'll ask a question. Which was from all the experiments that you did, which scenario struck you as one where drivers performed most poorly?
I haven't shown all the scenarios in this presentation, but I had a slide and then I deleted it. But there was one scenario where there was a parked truck on the side of the road. And then there would be a pedestrian that just jaywalks right when the ego vehicle was approaching that parked truck. And then this is where we saw a lot of collisions happen. Because drivers usually didn't expect someone to come from behind that parked vehicle. So although they would slam on their brakes very harshly, they would still collide with the pedestrian. Like, thank God it's not in the real road.
Your scenario.
I used to work more in heavy rail, but I still do a lot of heavy rail. And that's actually the #1 cause, not #1, one of the top causes for driver fatalities, actually, the level crossings, when there's trains going in both directions. And one of them passes and they go around the gate, they all check for a train going the other direction.
Yeah.
It's it's seemed in common.
Right.
So it's interesting that the same thing with pedestrians is more of a general lack of
Yeah.
something.
Expectancy. Yeah. There's no expectancy that, yeah. Yeah. Thank you.
Thank you very much to Alia. Next up, we have Milad Saidi. Milad is a PhD candidate in civil engineering here at University of Toronto. His research focuses on spatial prediction of traffic-related air pollution using mobile monitoring, computer vision, land use regression modeling. And he develops image-based traffic analytics and machine learning frameworks to better understand urban air quality patterns. Milad also did not provide a fun fact, but I understand he's a soccer player who's been recently injured and therefore could not take the position at Chelsea and decided to complete his PhD instead. So with that, I'll pass it on to Milad.
Thank you. Thanks, Matt, for the introduction. I'm a PhD student working with Marian Hatzopoulou, and in today's presentation, I present one of my papers. In this paper, we wanted to bridge the gap between data reproduction and doing true prediction. So for this paper, we used mobile data from ultrafine particle to predict long-term concentration. But this method can be applied to any kind of machine learning, any kind of data. At first, I will provide some introduction about machine learning, land use regression models, and then I will explain the methods that we used, and then I will present the results of our methods. When we talk about machine learning, we have different sensors that record a property. For example, these sensors. Then we install those sensors on a stationary station, or we install them on a mobile platform, and then we collect the data. We also extract some predictors, right, or features. And using the predictors and the sensor data, we train a model, and then using that model, we do some prediction, like whatever we think about, like traffic, air pollution, anything we can kind of record using the sensors. And we have seen like huge increase in number of publications that use machine learning in recent years. And also we know that real world data is autocorrelated. For example, this one is land elevation. And in autocorrelation has been ignored by many studies. But the question is that can we really ignore autocorrelation in our data? Because most of the models has been developed based on, especially the methods that use for overfitting. They assume their data is not autocorrelated, but real world data is autocorrelated. Also, we have this picture. The first guy is asking, this is your machine learning system, right? The other guy says, yeah, you port the data into pile of linear algebra, and then you collect your answer on the other side. The first guy is saying, what if your answers are wrong? And he answers, you just pile until they kind of look right. But this is something that we need to avoid. Also, we have this quote from a Nobel Prize winner, Ronald Koss, which says, if you torture the data long enough, it will confess to anything. And we have this funny reel from Instagram. The researcher says, like, we let the data speak for itself. But earlier that day, the researcher is torturing the data. Also, this is a picture of a horse named Clever Hans. This horse could do math, but this horse only could do math when the owner was present, when the owner was there, and based on owner's face could do kind of prediction, kind of do math. But the horse wasn't clever. Also, we have this paper, which is about unmasking the clever Hans predictors. In this paper, they had, they trained a model. And then in their model, they had a tag. Okay, I'm showing it on the picture here. They had a tag here. And then when they removed that tag, their model could not do prediction. For the first picture, when they had the tag, the model could do prediction. And then when they removed that tag, the model could not do prediction. And then they create an artificial picture of a car. And they put the same tag on the car. And then that car was classified as a horse. And then when they removed that, feature, that's kind of part of the image or that tag, the model could not do classification. Here I will explain a little bit about land use regression models because I'm going to apply the things that I just explained to land use regression models. In general, for land use regression models, we have several main steps. The first step is preparing data, pre-processing, preparing predictors from meteorological data, GIS data, images, and so on. For our study, we were dividing Toronto to 100-meter distance grids. And then for each grid, we were extracting predictors, let's say lengths of road in that point. And then the next step is feature selection. Usually people do feature selection to make their model easier to understand, easier to debug, and make it increase the performance. And also we have model selection. So people usually try different kind of architecture, try different hyperparameters to select best model that they can have. And then we have elevations. Usually people traditionally people were doing train test evaluation, but in recent year, people also do random cross validation for avoiding, for evaluation. Also, some people use random cross validation for avoiding overfitting. But as I explained, our data is sometimes autocorrelated, but we should ask if random cross-validation can avoid overfitting or not, if it's used during model selection. Also, in recent studies, we have seen using special cross-validation for evaluating environmental data. Okay. Oh, I thought you see this picture. Okay. So the explanation was for this picture. And then we have prediction. For our study, we installed ultra-fine particle sensor on a mobile platform, on an urban scanner. And we collected 34 days of samples. Our data were noisy, and we had a lot of noise. We were driving the car in the city, and we were recording data second by second. And this was the roads that we used during sampling. Also, our objective was to predict long-term exposure surface, long-term average concentration of ultrafine particle. But our data were second by second and using mobile sample, right? So we, apart from the data from urban scanner, we had 17 continuous and stationary sensor that we used for evaluating our model. And then we also extracted different features from GIS layers, from climate and meteorological features, air quality features from stationary stations, let's say a station in the Pearson airport. Well, and then we ended up with 200 predictors. We also did some pre-processing, and we removed the data outside of this range for removing outliers. And then we used XGBoost model to develop model. And then we did prediction. For developing XGBoost model, we kind of used 7 different modeling frameworks because we said we might encounter some problems. Also in real world data, apart from autocorrelation real world data, sometimes we have limited data. So it's another problem apart from autocorrelation. Also, to kind of see if our model can do prediction without doing any like pre-processing. If our model is robust toward pre-processing, we did 4 extra models. This times we just use different like outlier removal methods. For evaluation, we divided to test train because our data were mobile sample different in different days. We could have random cross-validation, special cross-validation, temporal cross-validation, and special temporal cross-validation. And this data was internal, but our goal was to predict continuous long-term, right? So we used 17 continuous sensors for validating final results of our models. First, as I said, we used different modeling frameworks. So we had aggregated data in Toronto, and we had our features. We had around 200 features. First, we used all the features that we had, and then we used random cross-validation to hyperparameter our models, to choose hyperparameter of our model. And then for the second modeling framework, we combined hyperparameter tuning with a special cross-validation. We then combined it with temporal cross-validation, and then combined it with a spatial temporal cross-validation. And then apart from having all the features, we combined feature selection with hyperparameter tuning with this evaluation methods. So we kind of used a couple method for feature selection, hyperparameter tuning, and this method of evaluations. For first one, we combined feature selection, hyperparameter tuning, and special cross-validation. For next one, combined it with temporal, and for the last one, we combined it with a special temporal cross-validation. And then we reported the metrics, as we can see in the first model. Okay, I have my in this model, we have overfitting. In this one, also we had overfitting, but this one and this one and this one, we avoided overfitting for train and test. This one, and this one. But we had different metric for them. Oh, what happened? And then we also reported different cross-validation metrics for each of them. And we saw a more balanced metric for these 2 last models. And to truly evaluate our model, we used continuous measurements from backyard sensors. And we saw for these last 2 models, we had better, for these 2 models, we had better, less error in our prediction. And to understand how our prediction is, we create surfaces for each model. Usually when we develop a model, we expect to see something linear like this, something actual value and like a predicted value. But I will show this might be wrong kind of understanding, especially for our data, which was second by second data, and our objective was long-term prediction. For the first one, we predicted this surface. We had artifacts in our surface, and also we had some weird maximum in our data. So we call this data reproduction. Maybe we are collecting data in rush hours, and because we just use rush hours data for a developing model, we see hottspot, unreal hotspot in our predictions. And we did same for each model, and we for this model, we still had those artifacts. But using this one, we could see some green areas. In green areas, we are expecting to see less air pollution. So for this one, we could see more roads and more kind of green areas. And then we added feature selection. We still had some artifacts. But for these two last models, which we called them true predictions, we had this kind of predicted versus actual value. And then if we compare this surface with the first one, we see huge difference. And for the last one, we see higher concentration on roads and lower concentration in parks or green areas. And then we extracted the feature importance for the worst and best model. And for the best model, we saw just relevant features were kept in the model. For example, road area, distance from closest highway, traffic, the things that were directly impacting air pollution, water area, park area, which had opposite impact on our predictions. So we made our model interpretable, which we believe it kind of should be applied to any other data as well, to make models interpretable and simpler to understand. Also, if you remember when ChatGPT was removed, it was giving us different answer if we were asking same question using a slightly different wording. So we were asking same question from ChatGPT, but our wording was slightly different. And then we were getting totally different answers. We wanted to test the same thing. So we wanted to ask our model same question using a slightly different wording, which we used outlier. We used a different outlier as our input. So first we used the outlier that I explained. Then we used 95th percentile as an outlier, and then we didn't do any outlier. And then we saw we have a more balanced metric for cross validation, and then we had also better result for continuous measurements and the surfaces. We saw in the second modeling framework, we were getting similar surfaces, but our first modeling framework were kind of biased toward noises. So noises were having impact on the model. And in conclusion, for real world data, autocorrelation should not be ignored. And also while designing training framework, we should think about objective of our model, and we should design our model based on our objective. Also for future work, we suggest, what if we train many models with different objectives, and then different objectives give us different features, and those features are meaningful, and then use those features to prevent extreme events like extreme traffic or whatever, or create a desirable outcome. Yeah, thank you.
Thank you very much, Malad. Or online. Okay, I'm interested. I mean, there's a lot of, you've spoken a lot about the many different features that you meaning from in order to predict ultrafine particles. Can you, are those interpretable features, or are they do you have examples of the key features?
So, okay, let me go back.
Like which ones were most important?
Just a second. Okay, so we have the two, let's talk about these two modeling framework. The first one, this one, and this one. For this one, we had distance from Billy Bishop. It doesn't make sense. Why distance from Billy Bishop should have impact on ultrafine particle in west of Toronto. But for this one, that feature didn't end up even in the model. But for this one, what we have? Road area, which is impacting ultrafine particle. Distance from closest highway, again, has impact on ultrafine particle. This is AADT, average traffic, daily traffic. This again has impact. Length of highway. And then water area, and it is opposite, like opposite impacts.
Any findings from these that you could say are like policy sensitive in some way? Like, would you be able to advise using a learning model like this?
So,
policy changes that might make improvements.
Say we don't want to see Trump. We create a model and our objective is not seeing Trump. And then we should have meaningful features first. And then we limit our features. And then based on those features, we kind of work on those features to not see that objective. So it depends on our objective. Yeah. Here also, it depends on our objective. If our objective is prevent like extreme events, first we develop model, we extract features. Here, feature is road area. If we kind of want to, if we had better features, if we had a type of cars, we might get better features, and those ones are more relevant. But for here was road area, and yeah. It depends on objective and the available features that we have. Yeah.
Thank you very much, Malad. That brings us to our fifth and final presentation. And Felita, are you here? Yes, there you are. Okay, excellent. Felita is going to be presenting Who Will Subscribe? Unpacking the Market for the Mobility as a Service in the Toronto area. Felita wins the award for the shortest biographical sketch. Felita is a PhD candidate whose research focuses on understanding preferences towards emerging mobility options. She loves to swim. Felita. Please a round of applause for Felita.
Thank you very much. Thank you, Professor Roda. The title of my presentation has actually changed, but anyways, I'm here to talk about the results of our research on understanding the potential market for emerging mobility from data that we collected here in the GTA. So first, what is emerging mobility? Well, when we talk about emerging mobility, we're often talking about autonomous vehicles, electric vehicles, or shared mobility or mobility as a service. And in this presentation, I'm just going to focus on the last two. So why do we want to learn more about emerging mobility? Well, because they may bring about numerous benefits, including improvements in terms of environmental sustainability. For example, the use of electric vehicles may reduce greenhouse gases, as well as improve air quality. And emerging mobility may also improve equity and accessibility to different destinations, especially for people who cannot or do not drive. And they may also improve urban planning and also efficiency with which people and goods move. And so researching the potential impacts and also the adopters of emerging mobility is important so that we can create evidence-based policy that will help in its implementation, but also in mitigating its negative externalities. So in our research, we basically did two separate surveys, and the first one focused on electric vehicle preferences. Our goal really was to understand the role that range extenders would play in electric vehicle adoption. And in contrast, or maybe in comparison to the more popular plug-in hybrid, vehicle, extended range EVs, which plug-in hybrids have a larger gasoline, it's a combustion engine vehicle, and it has a smaller electric motor and battery. In contrast, the extended range EV has a electric powertrain. It has an electric motor and battery and a smaller backup gasoline generator. To understand preferences towards these types of electric vehicles, we conducted a web-based survey, online survey. We administered it to residents of the Toronto area who intended to lease or purchase a vehicle within the next 5 years. And our sample size was around 500, well, it was 500 respondents after data cleaning. And a key component of our survey is the stated preference experiment, where basically we presented a hypothetical situation or a scenario to the respondents and asked them to select between 5 different vehicle powertrains, with extended range EV as one of the options. And these powertrains are then characterized by a set of attributes. These attributes essentially describe, the price, the operating costs, the electric range, the emissions of these vehicles, and then we ask respondents to pick which one they are most likely to buy or lease. The values or the levels of these different attributes are varied from one situation to another. And through this experiment, the idea is basically to capture the trade-offs that potential consumers would need to make in choosing a specific powertrain. Based on our data, we then developed some empirical models, and our model tells us the substitutional patterns between these different types of powertrains. And the substitutional patterns are relatively in line with what we would expect, with electric vehicles being more likely to be substituted with one another than non-electric vehicles, and similarly for conventional vehicles and also for hybrid vehicles. And what I want to point out here is that the extended range EV option is more likely to be substituted with both other hybrid vehicles and also the battery electric vehicle. We then predicted the market shares for each of the powertrains, and with EREV in the mix, we estimate that BEV, EREV, and PHEV will altogether make up about 57%. Yeah, 57% of the market share, which is a relatively significant proportion. And without EREV, or if EREV had not been available, we see that the largest increase in market shares would occur for the BEV and plug-in hybrid option. And that's a reflection of the substitutional patterns. So then we also computed the sensitivity to different vehicle attributes. And in this particular graph, we see the sensitivity to extended range EV purchase price. And this graph basically tells us the change in predicted market shares with respect to percentage change in EREV purchase price. And so as expected, when we increase the EREV price, we would expect its market share to drop. And on the other hand, when we decrease its price, its market share would increase. But what I found interesting was that consumers are demand for EREV is relatively elastic to its price. And with a relatively small reduction in its purchase price, for instance, a 20% decrease would allow it to overtake the market share of the battery electric vehicle. And so there is a clear market for extended range extenders in helping electric vehicle adoption. On the other hand, consumers, we find, are not as sensitive towards operating cost. We see a relatively flatter graph for the market shares. Even when we double the monthly operating cost of EREV, it's market share were only reduced by small percentage. Finally, we estimated potential consumers' willingness to pay for different attributes. For example, operating cost savings, additional electric range, charging time savings, and also emission savings. And what I want to highlight is that consumers value operating cost savings for the electric options more than they do for the ICEV or the hybrid electric vehicle options. And this kind of supports the idea that electric vehicle owners are willing to put down a larger initial investment or pay a higher initial price for long-term cost savings. And we also found that electric range is valued highly and higher than gasoline range. And so consumers are willing to pay more for additional electric range than for gasoline range, which kind of makes sense because electric range is often a limiting factor due to charging time, which we see here as well, that they're willing to spend quite a bit of money to save time on charging, and also due to perhaps infrastructure barriers. All right, so moving on to our study on shared mobility or mobility as a service. We did a similar survey, separate survey, but our goal for this survey was really to understand the extent to which respondents are willing to subscribe to a bundle of shared mobility services, which include scooter sharing, car share, local regional transit, ride hailing, and also bike sharing. It was also an online survey, but our sample size this time was quite a bit larger. We had 1,200-ish respondents. And again, we did a stated preference experiment, except this time we asked them to select between 3 different bundles of mobility services. And within the experiment, we asked them, we basically presented a volume of access to each of the modes that are bundled. And we also give them a monthly cost and ask them if they would like to subscribe to any of these plans or if they would like to opt out, so not subscribe at all. And again, we varied the volume of access from one situation or scenario to another so that we can again capture the trade-offs. And based on our data, we found out that we were able to estimate the factors basically that influence the propensity to adopt mobility as a service. And we found that individuals with higher educational attainment, individuals who live in Toronto, are employed full-time, are more likely to adopt. And in terms of mobility tool ownership, transit pass owners, bike share and car share members are more likely to also adopt. And interestingly enough, car owners are also have a higher tendency to subscribe. And this kind of tells us that maybe bundles of shared mobility services may complement private car ownership rather than replace them entirely. And similarly, frequent users of shared mobility are, as expected, more likely to subscribe as well. In terms of the predicted market share for mass in the region, on average, it's around 58%. Oh, the graph is quite blurry, but we also observed some variability within the subregions, and as expected, there's a higher percentage of people who are more likely to subscribe in Toronto and in York region compared to the other regions, essentially because of the availability of these shared mobility services in these 2 regions. In terms of sensitivity to monthly bundle cost, we found that consumers are not super sensitive to monthly bundle because doubling the monthly cost would only reduce the predicted market share from around 58% to maybe 40, 43% or 45%, so around a 13% decrease. And we also estimated, how much consumers are willing to pay for additional access to different modes. And what we found was that there is significant variability in the population in terms of how much they're willing to pay. And we found that, especially for local transit, regional transit, as well as bike share. And we found that bike sharing is by far the most popular mode to be bundled or to be included in a mass bundle. We found that consumers are willing to pay on average, 41%, $41 a month for unlimited access to bike sharing. And on the other hand, scooter sharing is not very popular. This could be because of the higher cost of scooter share compared to bike share. And so overall, our research tells us that there is a sizable market for emerging mobility, particularly for electric vehicles and also mobility as a service. And the propensity to adopt emerging mobility is affected by a range of factors apart from personal and household attributes. And these factors include mobility tool ownership, their familiarity with emerging technology, as well as their residential location. And one last thing I'll point out is that our data is a cross-sectional data, so it provides us with a snapshot of current preferences. But there is a need to continually collect, preference data to see how the propensity to adopt different mobility options may evolve over time. That's all. Thank you.
Questions? I think there was a couple questions in the chat. Put your cursor up to the top and click on the
Yes,
chat.
we have a question saying who's less likely to be an adopter?
Oh, can you repeat that question?
Who is less likely to be an adopter?
Oh, okay. Yeah, I can answer that. I can go back to my slide, maybe. Are you asking about electric vehicles or mobility as a service? Oh, do I have to type?
Yeah, you can just.
Wendy, can you please confirm? She said MAS, M-A-S.
Oh, okay. Yes, I will bring that up. So, okay. So, yeah, so different personal attributes like educational attainment, also employment status have an influence on the likelihood of adopting MAS. And so if these are kind of binary variables, so, those with higher educational attainment are more likely to adopt, meaning that those with lower educational attainment are less likely to adopt. And those who are not employed full-time, let's say they're retired or they're employed part-time, they're also less likely to adopt. And non-Toronto residents, so residents from, other sub-regions are also less likely to adopt. And there's not an exhaustive list, but these are some of the factors that influence the adoption. Hopefully I answered that one.
Thank you very much. Was there a second question on the chat?
No. I think
No?
they just
Okay.
sent their question into 2 messages.
Okay, thank you very much.
All right.
Shuyan.
Show me your, hold on. Math package.
Math calculation? Yeah, I purposely excluded that from this. Oh, yes.
I'm interested in this adoption rate for the math because from my understanding is that we could have various different math package, like mobility package, or with a monthly plan for the users to buy, and their preference is not only determined by the if they are open to this new technology, but also determined by the the combination of different mobility tools in your package. Right?
Yes.
Test like one set of the mobility package, do you find a way to differentiate the different preference regarding the service and or regarding the content that included in the service?
I definitely did not go into details in terms of how we designed our experiment, and hopefully I can discuss it in more detail. Yeah. So
also have the choice, don't want to just subscribe any, but he might be interested in a plan D, which is not included here.
Yes. So yeah, that's a limitation of the experiment, obviously. Like, if there is another plan that they want to subscribe to, it's not presented here, it's not an option. We can't estimate how many of those people are willing to subscribe to a different plan. But in terms of the modes that are included in the bundle, we did design the survey based on their current travel patterns and also their ability to ride bicycle, for instance, to ride a scooter. If they, in a previous segment of the previous section of the survey, we asked them all these, ability and also preferences. And so we then use that information to inform our design. So it's in a way kind of pivoted around their current travel patterns, including their current mobility tool ownership. So for instance, people who do not have a driver's license will not see the car sharing option. This table will collapse a little bit. People who cannot bike, they won't see bike sharing. People who can't scoot, they also won't see scooter sharing. So in that sense, we try to make it as realistic as possible for the respondents.
And also for the math, what is from your perspective, what is the motivation of people to use math? Is it because the seamless traveling experience? Like, for example, if I buy this plan, I don't need to download separate app for each travel mode, or is it because you offer a discount on the monthly cost, or?
Mm-hmm. I think there could be a variety of reasons. One of them is probably definitely what you mentioned, integrating all these different mobility options into one platform is definitely a motivation. I think mobility as a service was initially introduced, or the thought behind it was that it might replace private car ownership, which our data tells us that it might not necessarily replace car ownership, but it might complement it, or it might supplement private car ownership. But there are many different reasons why people would want to use mobility as a service and also just shared mobility in general. Maybe they live in a very dense area, there's limited parking, having a car, personal private car is not as feasible. And also for some people, they are not able to drive, for instance, they have to rely on transit. So there's a variety of factors, I think. Thank you.
Thank you very much. Is there any other questions? Yes. Oh.
Thank you, Felida. So I have a question about the willingness to pay. So as more and more employers asking their employees to go back to the office, so we've seen a lot of commuters back to downtown, and they park and ride. And the one result of that is that a lot of the parking lots on GO train stations are close to capacity. And do you have any evidence? Is there any evidence showing that people living close to those stations with parking bottleneck have higher willingness to pay than others?
People living close to park and ride. No, unfortunately, we don't have we don't have information that is that specific. I think we did the analysis more so at a sub-region level in this case. So I can say, you know, Toronto residents are more likely to use it, or I mean, to adopt, and also for willingness to pay. Like I mentioned earlier, there is significant variability in the population, but we can only estimate it at an aggregate level, not for you know, a specific individual, I would say. But I think that kind of reinforces, I think, the need to also continually collect data because things change over time. And as you mentioned, you know, circumstances have changed. And so it's likely that preferences have also changed. So yeah, but unfortunately, I don't think I can say for certain things.
Since you have this slide up, I'm interested in this scooter share. Do I infer from this that people would pay $19.40 to have scooter share removed from their package?
Quite counterintuitive. Again, I think this is because of this might be a result of the design of our experiment. We designed our experiment based on existing scooter share prices in the region, we actually made it a little bit cheaper already in our experiment, which I believe scooter sharing cost something like $30 per week if you want unlimited access in certain parts of the region, maybe like Oshawa or something. Depends on the service provider. But bike sharing, on the other hand, costs way less. And so I think this is just a result of, you know, scooter sharing, because if we remove scooter sharing, the monthly cost will actually also decrease. Yeah, and also a lot of people don't have experience with scooter sharing, given that it's so far mostly been provided through pilot programs, and so they're not widely available, and they're not actually legal, I think, in the city of Toronto itself. So yeah, I think that's why.
Thank you much, Felita. Thank you all. And I think that, well, why don't we give a big round of applause to Felita and all the other presenters. That was the last presentation of the day. And tomorrow, I would like to invite you to show up at 9. I think it starts at 9 o'clock, right? Is there anything before 9 o'clock?
Yes, we
9
start
o'clock.
at 9 tomorrow.
Excellent. We start at 9 tomorrow. And this will be the second phase of this joint symposium, which is on TAL, which is the transit related presentations. So I look forward to having you join us tomorrow morning at 9 o'clock. And I wish you all safe travels going home. Thank you.